Bonjour everyone, in this video I will provide an introduction to AirtypeLogger, a video-based keystroke inference attack targeting XR devices. Current attacks for the virtual keyboard typically require longer input data. In hidden reality, the keyboard range is determined based on the bounds of the typing positions. However, when the input process is short, the boundaries of the typing positions don't necessarily align with the keyboard boundaries. In semantic input scenarios, the below method uses a hidden Markov model in the first stage to infer keystrokes, requiring the targeted user to type over 100 words during each attack. In the second stage, a 3D Shen model, trained on the targeted user's data, classifies characters from video clips, but doesn't leverage sequence dependencies within the keystrokes. To address the long input requirement, AirtypeLogger focuses on deciphering users' short semantic input by analyzing the video. In AirtypeLogger, the input content is semantic. Because the input is short, we don't determine the keyboard boundaries, and the layout is determined according to the device model. We use learning-based methods to identify typing positions and infer the input from these positions. Importantly, this approach doesn't need the data from the targeted user to train the attack method. In our setting, the input content is semantic, because semantic texts usually have a one-to-one correspondence with their keystroke trajectories. For example, while the trajectories of SIF, DSJR, and FDHT may appear similar, as they can be transformed into one another through translation, only SIF is a semantic text. We assumed that with the dataset pairing keystrokes with semantic texts, we could train a neural network to infer texts from these trajectories. AirtypeLogger has two stages: detecting typing positions from the video and inferring semantic text from these positions. Since users can adjust the virtual keyboard size and position, and input lengths vary from 6 to 12 characters, typing positions don't always align with keyboard boundaries. This makes it challenging to determine the keyboard range or collect a dataset pairing keystroke trajectories with semantic texts for end-to-end training. Moreover, the diversity of semantic text fragments makes manually collecting large training datasets impractical. To address the unknown range issue, we propose a positional and scale normalization to eliminate positional and scale uncertainties of the keyboards. Furthermore, we introduce a synthetic keystroke generation strategy that leverages public text corpora to generate millions of data samples for training. AirtypeLogger has two phases: training and attack. In training, text fragments are mapped to key coordinate sequences using synthetic keystroke generation. A transformer-based network is then trained to infer text from the spatial temporal representation of the sequences. In the attack phase, the true coordinate sequences obtained from air-typing event detection are fed into the network to decipher the user's input. Notably, the text can be an incomplete fragment, like IGHTAA from Lightyear, and doesn't need to appear in the training set. Air-typing events are detected by analyzing hand movements. The fingertip moves slower during keystrokes and faster between keys. So slower regions in the heat map are given higher weights. After generating the heat map, the detection model locates the keystrokes and sorts them according to the order of appearance to form the true coordinate sequence. The true coordinate sequence is normalized to remove uncertainties about the keyboard's position and size. We then encode the relative positions and temporal order of keystrokes into spatial temporal representations, which are input into the transformer-based network. The network's self-attention mechanism allows us to use the full sequence information when deducing each key. The training pipeline is similar to the attack pipeline, except that text fragments come from a public corpus, Wikipedia, and key coordinate sequences are generated based on the keyboard layout. To incorporate real-world variations into the training set, we propose a positional perturbation strategy that adds noises to the key coordinate sequence. when the camera is not directly facing the virtual keyboard, but instead capturing from a side angle. The coordinates of the error typing events recorded on the image plane will differ from those on the keyboard plane. To mitigate the impact of this off-axis distortion, we introduce a rotational perturbation which rotates the key coordinate sequence during the training process. Our dataset includes two scenarios: a front view with a beta angle of 0, and a side view with angles ranging from -60 to 60 degrees. 15 participants contributed front view data, using text fragments from 3 different corpora. This data was used for studies on positional perturbation, temporal encoding, and method comparison. The side view data from 10 participants was used for the study on rotational perturbation. For keystroke inference, we used the character error rate, or CER for short, where a lower CER means higher accuracy. We conducted ablation studies on positional perturbation, temporal encoding, and rotational perturbation. In the left image, we can see that positional perturbation significantly lowers the CR of AirtypeLogger, with temporal encoding also playing a key role. On the right, rotational perturbation significantly reduces the CR when the angle is large. We compared AirtypeLogger's accuracy with existing methods, and found that its character error rate is significantly lower than that of other methods. It can achieve a CER of less than 0.1 with 7 observed error typing events. The detection model was trained on data from multiple users and tested on unseen individuals, demonstrating that AirtypeLogger can successfully perform attacks on users outside the training dataset. AirtypeLogger generalizes well to unseen text. In our experiments, 50% of the text fragments were not in the training set, yet most were accurately inferred because parts of them appeared in the training set. For example, as shown on the slide, RTM-ENT DOE isn't in the training set, but parts like RTM-ENT and DOE are, and some of them share the same normalized key coordinate sequences. The self-attention mechanism allows AirtypeLogger to focus on these familiar parts and ignore the influence of other unseen parts. AirtypeLogger mainly addresses the gap in video-based attacks for users inputting short semantic text, whereas previous works focused on longer inputs. To tackle the challenges of the unknown range of virtual keyboards and short inputs in videos, we introduce a positional and scale normalization, along with a spatial temporal representation that encodes the relative positions and temporal order of keystrokes. By leveraging the known layout of the virtual keyboard, we also propose a synthetic keystroke generation strategy and input perturbation, enabling self-supervised training using only public text corpora, like Wikipedia. We conducted extensive evaluations on real-world video recordings of different users inputting content in a virtual environment. Our results show that AirtypeLogger achieves high precision with just a few consecutive keystroke observations from various video angles. As discussed in our paper, when the input exceeds 6 characters, semantic texts and normalized key coordinate sequences usually have a one-to-one correspondence, making end-to-end inference feasible. However, for random input, no matter how long the input is, this correspondence becomes difficult to ensure. For example, SAFQ-WEX and DFG-WERC share the same normalized key coordinate sequence, making it impossible for a simple end-to-end model to infer text accurately. To improve password inference, we made 2 updates. First, we improved the normalization method to maintain the relationship between the x and y coordinates. Second, we introduced a mapping rule. During training, we assign each normalized key coordinate sequence to a reference text, such as the one at the top left corner of the keyboard. During testing, we search for strings with matching normalized key coordinate sequences. Using this approach, we tested AirtypeLogger on 1 million common passwords. Without ever seeing a complete password during training, it successfully inferred 60% of them in simulated scenarios.